Okay, in this lecture we want to discuss continuous random variables and continuous distribution functions. So if a random variable x and its distribution are continuous, then its distribution function f of x is given by the integral of the density function f of v. So I've always referred to this as probability density function, and this is probability distribution function, but different people use different terminology. This is called f of v because of a variable substitution, and because this is a mathematics book. In engineering, I would write this as little f of x dx, because it is the same variable. It's just this one is under the integrand, and some mathematicians do not like using the same variable. They insert a dummy variable, but just be aware that v basically is x. The integrand is the density of the distribution. It's assumed to be positive and it's continuous. And if we take the derivative of the probability function of the distribution function, then we get the density function, and vice versa. So our formula then for estimating that the probability of a variable lies between two values is obtained by taking the integral from value a to value b of the density function, or the probability density function. So obviously if we integrate the probability density function from negative infinity to infinity, we will get 1. Here is an example of a probability density function, and once again, gosh, I've always called this a distribution function, but never mind. So this is an example of a probability density function, little f of x. And so if we want to know that the probability that x occurs between a and b, what we excuse me, what we're really doing here is we're finding the area under this curve between a and b. So quite different from the discrete variable. So if we want to look at an example, let's say x has the density function little f of x is 0.75 times 1 minus x squared. If x is between -1 and 1 and it's 0 otherwise. So if we want to find the distribution function, then basically if x is less than -1, f of x is equal to 0. So we don't even have to start our integration until we get to -1. So the lower limit of our distribution will start at -1, and then it'll run up to the variable x. So we now are going to integrate our density function, and we come up with this result. So notice our probability function is just the integral of our density function, and that's only applicable if x lies between -1 and 1. If x is greater than 1, then the probability is equal to 1. So if we want to know the probability that x lies between -1/2 and +1/2, and so I want to point out very clearly here that the lower limit now, because this is a continuous distribution function, the lower limit is included. So x can assume the value of -1/2. It can assume the value of +1/2. That's because this is a continuous distribution function, and note that that's very different for the discrete distribution function. So if we substitute the limits -1/2 to 1/2, then rather than a function, we're going to get an actual number, 68.75%, meaning that the probability that our variable x lies between -1/2 and 1/2 is almost 69%. If we want to find the probability that x lies between 1/4 and 2, then we basically would look at the integral from 1/4 to 1. Why 1? Because remember, our density function is only defined from -1 to 1. So we have to stop at 1. So that would give us 31.64%. So if we were to try to calculate the probability that our variable is less than x, and we substitute in, we would get 0.95. If we want to know, for example, let's say we want to know at what value would we have included 95% of our distribution. So we would say, okay, we want to know what value of x we would get to 0.95. Then you basically would take your probability function f of x and your distribution function f of x, and you would set that equal to 0.95, and then you solve for x. So what you get out of there is x is 0.73, and you can then determine at what value of x would you have included 95% of your population. We can define the mean and variance for a random variable x and its distribution. Notice that we've now gone from the terminology S to the terminology sigma because we're basically talking about distribution functions as opposed to actual sample data. So there is a difference. A distribution function is theoretical. Actual sample data are experimental. So the mean is essentially the same definition, but it's achieved a slightly different way. So for a continuous distribution, you would take the value of x, multiply it by the density function, and integrate from negative infinity to infinity. That's going to give you the mean. When the mean is calculated in this way, it's often referred to as the expectation value, and it's sometimes often referred to as the first moment. The variance is basically sigma squared. In that case, we take x minus the mean, square it, multiply it by the density function, probability density function, and integrate from negative infinity to infinity, and that gives us the variance, also known as the second moment. You can calculate higher order moments, and we will discuss what higher order moments represent. But as a general rule, a moment is going to be a variable times the density function integrated over the entire range the density function covers when you're talking about a continuous distribution. In a discrete distribution, the definition is the same. The integral goes to a summation. The continuous variable x becomes the discrete variable x. The continuous probability density function obviously goes to a discrete density function. So this is our familiar variance. Take its square root, you get the standard deviation. So as we said before, the mean mu is also denoted e of x. Sometimes this is shown as x with triangular brackets. It's the expectation value of x because it gives the average value of x if you take many trials. Mu and sigma squared are called parameters. And as I said, they're sometimes referred to as the moments. We'll skip over that. So if you have a uniform distribution, so here is an example of a uniform distribution. So between 0 and 1, we have basically the value 1. And that's, so f of x is 1 over b minus a. If x is between a and b, f is 0 otherwise. So basically we can calculate a variance from that. Using our formula, we get b minus a squared over 12. Now, the interesting thing is, if you look at all of these distributions, they all have the same mean, but the difference then becomes in the variance. So, for example, in this distribution, the variance is 112. If we now make that shorter and fatter, the variance is 3/4. here's the probability function for both of them, and you know it looks the same. It's just one has a greater slope than the other to reach 1. So this one would have like a longer, what we sometimes would refer to as a tail, taking it longer to get to 1 than this one as far as looking across values of x. So variance is measuring something that we would refer to as spread. So as a general rule, the taller and thinner, then the lower the variance, the shorter and fatter, the higher the variance. Just meaning that you're going to have values spread out over a wider range than if you have not as wide a range. If a distribution is symmetric, then the mean is equal to c. So if it's symmetric about x equals c, the mean is equal to c. Here is a definition of a moment. So, and we'll look at the continuous distribution for our example. So the moment, the expectation value of any function, g of x, is basically g of x times f of x, the density function, integrated from minus infinity to infinity. And that just gives you the mathematical expectation value. So you don't have to be looking just at expectation of the mean or expectation of the variance. You can look at expectation of any function and get that out of the density function. So because we defined our mean as just the x f of x dx, and that was the first moment, we can define the kth moment of x as x to the k f of x. And the kth central moment of x is x minus the mean to the value to the k integrated over the density function. So we have moments and we have central moments. Obviously the central moment of the mean would be 0 because the mean minus the mean is 0. So the first central moment is 0. The second central moment would not be 0. It would be the variance. So the first moment is the mean of x. The second central moment is the variance of x. And there are some higher order moments that sometimes can be interesting as well. And they measure different things. Variance, as we said, physically, variance is going to measure the spread of the data.